Hey guys, I'm back with video 3 of this week. So video 3 is going to be really dealing with applying the properties of linear transformations. I'll be giving some examples of this. And I'll be proving that a solution is linear using these kind of properties of linear transformations. So here's where we're going to start out. We've got a transformation t of x equals a times vector x from, you guessed it, R m to R n, right? We want to find the relationship between t of vector v, t of vector w, and t of vector v plus vector w. So the first thing I want to point out to you is that this is directly trying to get you to think of theorem 1.3.10, something that I probably did not label as that before, but it was basically that theorem that was talking about, if you've got t of x plus t of v, it's the same thing as t of x plus v. Stuff along those lines. So it really just wanted us to be reminded of that, I think. So if we know that t of vector v is a times vector v, t of w is a times vector w, then that means that we can also say that t of vector w plus v plus w is the same thing as t of vector v plus t of vector w. So I really just wanted you to think about that. The second thing that it wanted you to think about applying these rules that we already know about linear algebra, these properties, is the relationship between t of v, t of kv. This also applies to the theorem, to that part of that theorem. You can look back at that if you're confused. But, if we use the rule again, we can say k t of v, that this is equal to k times t of v. So we can say like t of v, that's t of v. So the relationship here is that we're multiplying t of v times k, right? So what is my point in saying all of this? Basically, their point is that for any linear transformation, these two properties are true. And they want to write a proof about that using the converse of that idea. What I mean by that is, so we've got theorem 2.1.3. So transformation from a transformation of t from space M to space R is linear if and only if A, this law that I just talked about, is true, and B, this law is true. There's kind of a fancy way to prove this that I will sort of go through here. So basically, if we work backwards, if we start with t of x is t of x1, x2, all the way down to xm, that means basically that we've got t times x1 times e1, right? Because we've got, the entry that we're actually dealing with and the vector, right? Then we've got plus x2 e2 plus all the way down to xm e m, right? Well, we can then use the law that we already had to say t of x e e plus t of x2 e2 plus go all the way down the line to t of vector of x times vector e m. Then, so that was, clearly by property of A, right? But then we've used property of B because we say x1 times t of e1 this is by B. Now that we know this, now that we have it in this form, we can finally convert into okay, so if that really confused you as to why we needed to prove this, basically what it's saying is that, if we start out in this form, the only way to get back to this form is by using these two laws, right? We start out with, if we start out with it in this form, we've got T of, the different columns of the matrix and the different components of X. The only way to get back to the initial, to the initial setup is to use the two properties, so if we have to use the two properties to convert between these two forms of the equations, then obviously, a linear transformation has to abide by these two properties. So that was really the basic idea there. So that is video 3. Now, if you're wondering how long I'm going to continue saying that there's going to be another video, I swear video 4 is the last one. I will see you back here in a couple of minutes.